starting to arrive, so let's get started. So welcome back, everyone. This is the second summer session of the Ultra Quantum Matter seminar. Today we have two speakers again. Our first speaker is Xiangyu Cao from UC Berkeley, and he'll tell us about low-rank SYK models. So go ahead, Xiangyu.
Thank you, Matt. Thanks very much for the invitation. So very happy to be here. So my name is Xiangyu Cao. I'm a postdoc since a few years at UC Berkeley. I've been working quite a lot with Ehud. And so today I'm going to talk about work with Ehud and student Jaewon Kim, who is now in Korean military service. So expect to hear from him again in about 1 year or so. Yeah, so the talk will be about the family of generalizations of Sachdev-Ye-Kitaev models, which we wrote about in this paper, in this PRB here, in this recent preprint. So I guess the audience here is relatively familiar with Sachdev-Ye-Kitaev, but let's do recover this. So I don't know if SYK qualifies as ultra quantum matter, but it certainly qualifies as a pretty popular model. So it's the Hamiltonian, as we all know, describes the quartic interaction between some fermions, usually in quantum dots. So that's been interesting to diverse communities. For example, for high energy physicists, this has been a simple model of holography to study black holes and wormholes, problems in gravity. For quantum dynamics people, it has a remarkable property of being maximally chaotic or having so-called faster scrambling of information in a quantum system. And for condensed matter community, it is a interesting model to study low energy quantum states with no quasiparticle excitations. However, from a condensed matter point of view, it also has a couple problems. So the first one, quite obvious one, is that this Hamiltonian is unstable to quadratic perturbation, so hopping, which is almost always present in real models. And whenever you have this perturbation will become relevant at low temperature, and you will have instead a Fermi liquid, so destroying this non-quasiparticle non-quasiparticle state. Another point is that this model, so this Hamiltonian here, this quartic interaction, is very hard to realize. It's so hard to realize that it is almost unphysical. So to explain what I mean by this, or to qualify it a little bit, let us be more concrete and consider a recent proposal for realizing SYK model in a lab. So that was in an interesting paper by a group of Marcel France. So they proposed using graphene conflicts with irregular boundary, so drawn here, and you apply a perpendicular magnetic field, so that you have Landau levels, so many degenerate orbits, and then the idea is that if you look at the lowest Landau level, and you project the Coulomb interaction to the orbitals in that level, then you will get a Hamiltonian which looks pretty much like Sachdev-Ye-Kitaev. So you will have this quartic interaction. So remember that because you project it to the Landau level, you don't have quadratic interaction because it's a flat band. And so these Fermi operators are now associated with single particle modes in the LLL, and then these coefficients, they are made of this. So you have some overlaps between of single particle modes in this lowest Landau level with sites, and then you have Coulomb interaction here. Okay, so it looks very nice. However, we can ask whether this is really Sachdev-Ye-Kitaev model. So for this, let us consider this JIJKL. So it's a huge tensor with n to the 4 numbers, more or less. So let's consider it as a matrix of size n squared times n squared. And then you can realize that if I group this I and j and k and l respectively together, I can rewrite this matrix like this. So it's almost a singular value decomposition or angle decomposition, and you will find that there are only a proportional to n non-zero angle value or singular values, which I call lambda n here. Whereas in SYK model, these Ji, J, K, Ls are independent random variables. So then you have a full matrix of n squared times n squared, so you have a rank of n squared. That's a huge difference. And if you think about it a second, you realize that in any real systems where your fermions or your spins are interacting via some Coulomb interaction or mediated by some photons or phonons, it's very hard to realize a rank which is much larger than the number of constituents, and this extensive rank, so R being proportional to n, is more or less the most natural thing that you can realize, or maybe the best that they can do. So that raises a natural question: if we have a structured matrix with rank n instead of n squared, how that would affect the low temperature fixed point of SYK. Okay, so that's more or less the question that I want to address in this talk. So there will be roughly 3 parts. I will first go discuss the solution of the low rank SYK quantum dots, which we will see will have several different types of low energy states, including fast scramblers, non-Fermi liquids, and Fermi liquids. Then,
sorry, please go ahead.
Then I will say a few words on scrambling, in particular in scrambling in Fermi liquids and non-Fermi liquids, and compare with quasiparticle decay rate. Then we'll talk about some ongoing work on lattice models. Okay.
Yeah, I want to ask about the proposal. Why did they need to have irregular boundary?
Oh, I guess that's so that these wave functions are irregular, so are randomish.
Then why do I just use the usual gallium arsenide with some disorder?
I don't know about the specifics of the experimental setup. Maybe disorder is harder to realize. I'm not sure. That's their proposal. So they realize randomness by irregular boundary. I guess you can do that in other ways, but I don't comment on that.
Mm-hmm. Also, Coulomb interaction is not that non-local.
Coulomb, yeah, it is non-local.
It's not that non-local. It's not as non-local as SYK, right?
No, no, it is not that non-local. However, when you have projection to lowest non-level, maybe it arguably becomes more non-local. So I guess maybe, yeah, this is a very good question. Thank you for that. So what I'm pointing out is one say flaw in their analysis or their mapping from this realistic model to SYK, and I guess you could argue that there are other loopholes, which, for example, includes the Coulomb interaction being not long range enough, but I'm not going to address that. I'm just going to analyze the effect of the rank of the interaction matrix. Okay. All right. So now let's define this low rank SYK model, the dot model, which is motivated by previous argument. So instead of writing GI-GKL, I would write the Hamiltonian as such. So I would write it as a combination of squares of fermion bilinears, and these bilinears are all random bilinears with random coefficients, independent coefficients normalized appropriately. So as I said, and then as we will see, the most interesting physics happens when the rank of the matrix R is proportional to the number of fermions here. And I guess the standard way to deal with this kind of model is to decouple using introducing Hilbert-Stone-Rich bosons, and then you can basically view the interaction as being between a pair of fermions and one boson mode here, labeled by the coupling strength lambda n. Now we also assume that these coupling strength lambda n form a distribution which has a smooth limits when n goes to infinity. So I want to record that this is we are not the first person to introduce this model. Indeed, special cases of this model have been studied previously. For example, by Zhenbi and the collaborators in Chen Keshi's group a couple of years ago, and also by Estelis Shmarian and other people, who consider the special cases of the distribution of the coupling constants, whereas we are going to do a more systematic job in analyzing the possible low energy states, which will depend on the distributions we will see. Okay, so as usual, it's a large N model, and it can be exactly solved by dynamic mean field theory, also known as Schwinger-Dyson equations, which describes large N saddle points of the action. So you can understand this quite well pictorially. So here is this wavy curve is a boson propagator, this Hilbert-Stone-Rich boson. So it is either bare boson or comes from a self-energy, which is a fermion loop. So this straight curve or line is a fermion loop, and the dot means dressed, and also dashed curves means disorder averaging. So this D is a boson propagator, and it is given by a boson self-energy, which is fermion loop, and also a fermion is also coupled to a boson like this, so that the fermion self-energy is given by this. So now the first thing you realize is that if you have many more bosons than fermions, or if the rank is much larger than the number of fermions n, then you can basically integrate out the bosons and get back SYK4. So there's nothing new here to be discovered. Also, if there are far fewer bosons than fermions, then these bosons will not matter in the large N limits unless they form a condensate. And when they form a condensate, so you have a constant term here, so then the condensate will generate a SYK2 type random quadratic term. So in this case, you will have just an SYK2 type model, which is non-interacting. So the only new interesting physics happens when the rank is proportional to n. So these are the new quantum states that we want to discuss. So to further discuss that, let us rewrite the Schwinger-Dyson equations a little bit. So here my fermions are coupled to a lot of bosons with different coupling strengths. So it will be convenient to introduce a weighted sum of boson propagators like this. And this sum has two parts. There will be possibly some condensed bosons, which will have a zero frequency contribution, and then you will have some normal bosons, which is an integral over the distribution. And here the shape of the distribution will become important. Most specifically, the shape of the distribution near its maximum, so near lambda max here, will be important because it will determine how this term, how the singular part of this term behaves, or in physical terms, how the soft or almost condensed bosons behave. So in general, you can assume we can consider a large family of distribution edges indexed by exponent eta, and you can distinguish at least between eta larger than 0, where this distribution vanishes, and eta smaller than 0, where the distribution blows up. And we will see that the boson condensation can only happen if the distribution vanishes at the edge. That's basically because if you have very few bosons near the edge, then these bosons stand out, and they have to condense. They are driven by this Fermi loop to condense. And in this case, we'll generate a SYK2 term, and the rest of the bosons will be not that relevant, and we'll have a Fermi liquid. Otherwise, if there are so many boson modes, then there will be frustration. So you don't know which boson mode will condense, and then you will have non-Fermi liquids and fast scramblers. So that's a summary. Let's maybe go over different states we can obtain. So first, we can obtain some faster scramblers, and these are not that new. They have been discovered in previous papers that I have cited. So the fast scramblers come with two classes, which we call the class 3 and 4 for historical reasons. So in class 3, the distribution has a delta peak at the maximum, and in class 4, there's no positive lambda, so there's no possibility of boson instability to condensation. So if lambda is not all negative, then nothing can happen in this denominator here. Okay, and in both cases, you can show that no condensation happens. Here it's impossible. Here in class 3, you have so much frustration, you don't know where to go, and you have conformal solutions in both cases, and the scaling dimension of the fermion will be tunable as a function of the rank over the number of fermions. So you can have any number between 0 and 0.5. It's a bit like SYK-Q model for those of you who know what it is. And for all of these, you also have a maximal Lyapunov exponent saturating the low energy bound, lambda L equal to 2 pi t. And in particular, the graphene example that we discussed plausibly falls in class 4 because the Coulomb interaction is repulsive. So you can show that the lambdas that you obtain are all negative, and also it contains some n equal to 1 supersymmetric SYK discussed by Subir, Sachdev, and collaborators. Now, class 3 has also been discussed, and it features the so-called self-tuned critical bosons. So you have many bosons over here, and although none of them condenses, they are all soft and critical, and they also have a conformal solution. And as shown by Estelius Schmalia, in class 3, you can also have a superconducting instability, which is not included in this solution. This is a normal state solution. So, but as you see, these two distributions are quite non-generic. So here you cannot have anything here, and here you must have a delta peak here. What about more generic distributions? Well, we show that in these cases you have essentially Fermi liquids or non-Fermi liquids, but which are not fast scramblers. So I think I'm running pretty out of time. When did we start?
You're doing okay. You have 10 minutes left actually for your half hour. We started
Okay.
at 2. Yeah.
Yeah, good. Yeah. So in these cases, you have Fermi and non-Fermi liquids, which we call class 1 and 2. So we can show that both of them are accessible by perturbing a free thermal SYK solution, SYK2 solution, because in both cases you will have a condensate or effective condensate. Now in the Fermi liquid case, you can show that you must have a true condensate below some finite critical temperature, and then it will generate SYK2. So you will get a semicircular more or less as a spectral density, and you will have some quasiparticle decay, which qualifies the state as a Fermi liquid, although a bit anomalous. So this is for eta larger than 0. So with a vanishing edge. Now for eta smaller than 0, you can still do perturbation theory, because although there's no condensate for non-zero temperature, because you have so many bosons here, they can generate a SYK2 term just dynamically. So you get still this kind of spectral density, but now you have a dent given by this self energy, which is much larger than omega. So this qualifies the state as non-Fermi liquid. Now, so as I said, for this non-Fermi liquid, you have a quote unquote quasiparticle decay, which is much faster than temperature, and it's a bit like a coupling to a super ohmic boson bath. So you are damped very fast, and as a result, you can show that in this non-Fermi liquid class, you can have a normal specific heat, which is larger than the Fermi liquid case, which is proportional to T. And in particular, if you go to eta equal to -1, then this edge will become a delta peak, and you will develop a residual T equal to 0 entropy that we can see in class 3. Okay, so that concludes this first part, which is the largest part. Now, let me say a few words about scrambling in this model, in particular in non-Fermi liquids and the Fermi liquids case. So by scrambling, I mean computing this, the Lyapunov exponent defined by out-of-time order correlators. And there's a standard method developed by Kitaev and other people, which consisted in analyzing ladder diagrams or analyzing the angle value of the ladder diagram. So this is just general picture. This correlator is given by a sum of ladders where you stack some ladder kernel, and to compute its exponential growth rate, you want to find the largest angle value of the ladder kernel, and with this kind of angle states, and require that this angle value be 1 by adjusting lambda L, then you can find lambda L. So the ladder kernel in our case is basically, you have two kinds of ladder kernels. You have fermions coupled to bosons, and also you have this kind of boson fermion loop. So you have two kernels, and the equation we want to discuss is like this. So now in class 3 and 4, as I mentioned, you can do a computation which is really similar to SYK4 computation, and it gives you a maximal chaos, lambda L equal to 2 pi T, quite directly. But now in class 1 and 2, it's kind of new. You cannot do the computation with only conformal solution, because that will give you only 1 as a kernel. So it will not suffice to find lambda L. So you have to look at the effect of quasiparticle decay and interactions, which will give you this kind of contribution to the kernel. And this can be computed perturbatively. And the perturbating parameter is the rescaled rank appearing in this distribution. And you also have a kinetic term, which corresponds to I omega in the Fermi Green function. Then you solve this equation, you find that lambda L is given by this. So now what happens in Fermi liquid and non-Fermi liquid? So it's the same equation. In Fermi liquid, what we will see is that the right-hand side is very small. It's much smaller than T. So you find that lambda L must be very small compared to T. Then you can approximate this thing here by 0. So remember that K is the most positive eigenvalue of this non-trivial part of the kernel. And then you will find that lambda L is proportional to something much smaller than linear in temperature, and it's also perturbative in coupling constant. Whereas in non-Fermi liquid, it's the opposite. This term, because eta is smaller than 0, this term is the right-hand side is much larger than the left-hand side, which is proportional to T at most. So you can neglect the left-hand side and require that the left-hand side be 0 to determine lambda L. And in this case, you find that lambda L is linear in T. However, the proportionality constant is a function of this eta, which determines the power law of the distribution, but not coupling constant. So it's more universal, but not completely universal like in fast scramblers. However, it does approach the fast scrambler value when you approach class 3 as expected. Yeah, so that's the summary of the second part. So you have Fermi liquid to non-Fermi liquid to fast scrambler, and you can see that in Fermi liquid, the exponent, the Lyapunov exponent is more or less the same as a quasiparticle decay, whereas in other cases it's proportional to T, and you cannot really speak about quasiparticle decay because there's no long-lived quasiparticles. Okay, so just to wrap it up, let me talk about some ongoing work on lattice models, lattice versions of this model. So basically, you have the same type of physics, but on lattice. So you have a Brillouin zone, and you have fermion hoppings, and you have fermions on a lattice coupled to some bosonic mode, which could be phonons. So you have the same Xiangyu-Cao equations, but now with momentum dependence. Now, of course, now you have the Fermi surface. So you want to understand what happens to the Fermi surface, and you also want to understand how the bosons become condensed, whether they condense, and near which wave vector. So let me just discuss some of the cases because it's ongoing work. It's kind of incomplete. So let me restrict to the case where all the coupling constants are the same. So you have a class 3 like distribution. And noting that if you have non-generated distributions, we see you will get more Fermi liquid behavior. And let's also restrict to 2 dimensions and ignore superconductivity for simplicity. So you can have, the first thing you can have is condensation near wave vector 0 for the bosons. And in this case, what you can have is this kind of phase diagram at 0 temperature. So as a function of the coupling constant, if a coupling constant is larger than some critical value, then the boson can condense at zero momentum. And then remember that this Fermi surface is not just one band, but many degenerate bands corresponding to different flavors. And because you generate a SYK2 term, which is more or less, which is on site, you will hybridize these bands and split them. So you will get something like that, and it will give you a so-called Fermi ribbon. So you don't have just one Fermi surface, one Fermi surface, but many Fermi surfaces, which form a continuum. So in this ribbon phase, you can you can show that the coupling to boson gives rise to a marginal Fermi liquid, whereas at the critical point, so when the boson is about to condense, you have a non-Fermi liquid critical point which has this omega to the two-thirds self energy, so it's not Fermi liquid. And so this is, I forgot to put it here. This is nothing but the random phase approximation solution of Harper and Lee and collaborators in the 90s, I guess. Now you could also have another situation where you have Fermi surface nesting. Then you get different kind of ribbon, because you couple points of different energies. And in this case, there's no critical point because you always have a condensation. But in the condensed phase, you will have a marginal Fermi liquid. There's ongoing work, and there are a couple interesting questions that we can ask. For example, can we study hotspots version of this model, and what about transport and the superconductivity instabilities and so on. So I guess that's it. So I'm happy to take your questions. Thank you very much.
Okay, great. Thanks a lot, Xiangyu. Are there any more questions?
Yeah, I have a question here. So I wasn't really, okay, so one quick thing is when you calculate the Lyapunov exponent and the 4-point function, do you consider the mixing between fermions and bosons, or
yes,
always for fermion?
So the definition of the Lyapunov of the 4-point function.
Yeah.
Right. So now I only consider the 4 fermion OTOC.
I see.
Now, but however, if you look at these kernels,
yeah,
they will become bosons, right? So in the ladder, you will get fermions will become boson and come back. So if you can consider also mixed or boson 4-point function, and I think you will get the same thing.
Okay.
Because
so
they will be generated. Yeah.
Yeah, because naively, I would imagine that you would have sort of a block structure where some of the blocks are like fermionic stuff, and then some of the blocks are bosonic stuff. I think that would be more explicit if you'd go for the SOCI SYK. Right there, you would have an extended kernel, including the boson as well. But I guess your claim is that it's gonna be producing the same Lyapunov exponent.
Yeah, I think we have. So you do have bosons. The bosons are in the mix.
Sure. Okay. You just say that ideally one would maybe diagonalize the whole matrix and find a maximum. But here it seems like it's looking into a diagonal block. Not sure. Maybe it's the same.
Yeah. So if you can describe this as a kind of 2x2 matrix, right? So this KB can go from fermion to fermion, and but this guy is actually a product of 2 kernels. Correct. From fermion to boson and boson to fermion.
Correct.
So now I'm pretty sure that if you try to look at this 2x2 matrix and look at this eigenvalue, you'll get the same thing.
Sure. Okay.
Because it's like a bit like Markov chain, right? It's the same. They are the same paths. You just break it up furthermore.
Mm-hmm.
Okay, there's a few more questions. Subir, please go ahead.
In one of your slides, you had, I think it was a second to last slide on the main part of the talk. You had, go back. Yeah, one more forward. Yeah, so the middle column, 3rd row. So you seem to have some quasi-particle decay rate that's faster than temperature with 8 or less than 0. So how do you define that?
Yeah, so this is a little bit ill-defined. So let me go back to this slide and explain to you what I mean. So it's just this. So strictly speaking, there's no quasiparticles. They're destroyed by this self energy. However, if you look at the Green function, it still has this sign of omega, which comes just from random matrix theory.
Yeah.
So in this sense, you can still do perturbation. So this self energy is still small compared to the sign of omega. But there's no quasiparticle. This is a slight misnomer here.
Okay, thank you.
Yeah, what I mean is sigma omega is omega to this power. That's it. Or yeah.
Lujin, do you want to go ahead?
Yeah, thanks. So in the second last page or third last page, you mentioned there's a Fermi ribbon phase. Is this ribbon stable?
Yeah, this ribbon is a large N effect. So in the large N theory, it is there, and it is and then you have marginal Fermi liquid excitations in this ribbon. But whenever you go away from large N limits, if you have finite N, then at low enough temperature you won't have really a ribbon because there's no continuum, and you will just have some Fermi liquid with broken symmetry. So you have some split bands, not really.
Also, maybe another question. So for the original Sachdev-Ye spin model, should I view it as a model with rank n?
Yeah, it's a very great question. I think so. I think, yeah, I believe that I believe that its critical point would be more better described by a Lowrank type model. However, there's a long way between the original model and the Fermionic version. I think there's also there's large M and a large N, right? The number of spins and also the number M in SUM, and that M becomes the number of fermions in the Kitaev version. So I guess it's a bit hard to say very precisely whether Lowrank is directly relevant there. But speculatively, I think this is perhaps correct. Yes.
Okay, thanks.
Okay, I think it's a good time to move on to the second speaker. So thanks again, Xiangyu. And